Welcome. What we have seen till now is that WHT, which is defined as 1 over h phi of t plus h minus phi of t minus W of t. So this term, okay, what we would like to show that this goes to 0, okay. Why? Because if we show that this goes to 0, then that asserts that phi is differentiable, because this is the finite difference, and then we will also confirm that the derivative is nothing but W. Okay, so this is the thing what we are going to prove now in few steps. So we recall all the relations here in the same slide so that we can use those to manipulate some terms here. So here phi is satisfying this integral equation. Phi of t is equal to capital T of t minus Sx plus integration small s to t capital T of t minus r f r phi r dr. Okay, and g of t is defined as capital T of t minus s f of s comma phi s plus a capital T of t minus s x plus integration small s to t capital T of t minus r del t of f of r phi r dr. And then we also remember that the definition of WHT, this is this fraction minus WT, and WT satisfies this thing. Integration is equal to GT plus integration s to t capital T of t minus r br phi r w r dr. This is an integral equation, okay, so which is satisfied by W. Okay, so this W appears in WH expression. So we would like to show that WH goes to 0, basically, correct? So what we are going to show actually is that after many manipulation of terms, we are going to show that this satisfies the sufficient conditions for Gronow's inequality, and then that would assert that WH is going to less than or equals to some term, and that right hand side term we would be able to show that that goes to 0. So that is the main idea of the proof. So here phi of t plus h I can compute from this expression. Phi of t is written this way. So phi of t plus h is capital T of t plus h minus sx plus integration small s to t plus h capital T of t plus h minus r f r phi r dr. So here phi t also has this expression. So when you take the difference, term by term difference, we can discuss. First difference of this first term, and then we can talk about the difference coming from the integral term, and then of course the full expression of W also. Okay, W also solves the integral equation, so there also we have two terms. Okay, so those are the things we are going to, and W involves G, and G also involves, G constitutes 3 additive terms, 1, 2, 3. So there will be many terms now. So WHT is equal to this, okay, so phi t plus h minus phi t, this difference I am writing down now first. 1 over h is there, so you should not forget about it. So 1 over h, so here for this capital T of t plus h minus s, t plus h minus s is coming. So phi t, okay, so here capital T of t minus s, capital T minus x difference. And then this term is coming from G actually, because here W has G term, but here W is coming with a negative sign. So minus of this term would be present here. So minus a tt minus sx is coming from that thing. Okay, and now for the difference of integral term coming from this phi t plus h minus phi h, we are writing down now. So integration here is to t plus h first, because it's coming from t plus h, is to t plus h. All the places where t appears, I should write on t plus h, capital T of t plus h minus r f r phi r dr. Now from this term phi t, I would have just this integration, so I'm writing just this integration with the negative sign here, so negative sign here, minus integration s to t capital T of t minus r f r phi r dr. Okay, So far this term, this difference is concerned, all the terms coming from this I have written, and for W term only I have written this term. We still need to write down these two terms and also the integral term which appears in the equation of W. So we do this. So these three terms we write down now. So this first we write in the first term. So minus capital T of T minus S Fs phi S, and then this term minus integration S to T capital T of T minus R del T of Fr phi R dr, and then W, since W involves integral equation, this whole thing. So this whole thing with a negative sign should also come there. The T minus R B W dr. So that we write down here. Minus capital T minus R B W R dr. Okay. So WHT is written in this way. Okay, so there are so many terms. Okay, so but some terms I have combined to make a parenthesis because those terms are easy to manage. For example, I have taken parenthesis in the okay, for these three different terms. So here this difference divided by H. We know that since x is in the domain of A, and then this is differentiable, and the derivative of ttx is attdx, that appears here. Okay, so t minus s plus h and t minus s. So this difference is going to give me capital T of t minus s x. Okay, a t by t minus s x. Okay, or t minus s ax. Okay, so that is exactly this term. Okay, so as h tends to 0, this first term goes to 0. Okay, so that is the reason that I have just jumbled around few terms. So that I have written this term first here. Okay, for remaining terms also we need to do some sort of rearrangement so that we can group them together to some small terms, so which you can show easily those goes to 0. Okay, so that we do next. So next onward, I am not going to write down this in details. I will just replace this by term 1. We call this term 1, and we know that this goes to 0 as h goes to 0. Okay, we are going to use that. So WHT is equal to term 1 plus. Okay, so this whole thing is term 1 plus this thing, 1 over h, this thing. So now for this term, we can do a little bit more thing, because these two things quite looking similar. Okay, only difference is that it is s to t plus h, and here t plus h appears. Okay, but one can of course change variable. Okay, so substitute r minus h as r primes. Okay, so then r is equal to r prime plus h. So I would get f of r plus h phi r plus h here. Okay, and here I would get capital T of t minus r. Okay, and then the limit would also change. So when r is s, r prime would be s minus h. Correct? Okay, so and then when r is t plus h, r prime would be t. Okay, so this s minus h to s is the additional term. If we separate that, then I would get the, decompose the domain of integration, then I'd get one s to t here, s to t here, that we can manage, because then this operator tt, this looks similar, because here I would not get h here. Okay, so that is the main idea. So what we do is 1 over h s to t, capital T of t minus r, that is common in those two terms, so we take common, and then the difference of the remaining terms. So here I would get f of r plus h phi r plus h, here f of r phi r, so this difference would appear there, and then so f of r plus h phi of r plus h minus f of r phi r dr. And as I told that while doing this substitution, we do need to do decomposition of the domain of the integration. So here I need to separate integration s minus h to s there, and there if I back substitute it again to the old thing. So basically here it is nothing but s to s plus h, this integration. So that is the thing. So I write in s to s plus h, capital T of t plus h minus r f of r phi r dr. and then 1 over h is not forgotten, so it should be there. 1 over h is there. Okay, so from here we are going to get this this term, and then we are writing minus the next term. So next term is here. So after this difference, we have this term minus capital T of t minus s f of s phi s. So we are writing capital T of t minus s f of s phi is this term. Okay, so these two terms we are now clubbing together. Okay, and we call this term 2. Term 2. Why do we call this? And because this is very easy to manage this term. Here, if we see very carefully that here capital T of t minus s fs phi s appears, and here this 1 over h, this is like a mean average. Okay, s to s plus h and over h, this thing. And then we know already that continuity of this integrand, since the integrand is continuous, so this s to s plus is 1 over h, as h tends to 0, that it converges to that value where of the integrand where this r would be replaced by s and h should be replaced by 0. Okay, so that means capital T of small t plus 0 minus s, that means capital T of t minus s f of s phi s. So that is this. So in other words, this integration converges to this thing as h goes to 0. So all these convergences we are talking about in the Banach space norm. Okay, good. So this is term 2. Okay, and then but we still have many other terms, so this term is there, and then the remaining term. So I talked till up to this thing. I have not yet talked about these two terms, minus s to t. So this, in one place I have partial derivative of f with s to t, and another place b. So that's these two terms minus capital T minus capital T of t minus r, because this is common. Okay, t minus r is common. Only these are not common. So we would have this additive sign. So minus sign integration s to t capital T of t minus r del f del L t of f plus b r phi r w r dr. Okay, so wht has now this reduced form where this term 1 and term 2 are assured to go to 0, and we still have 2 more terms. Okay, so to deal with. Okay, so we now analyze the remaining things. So now we are using the d. What is the d thing? D is about w and w2. So here you see that f of r plus h phi r plus h minus fr phi r plus h, and then fr phi r plus h minus fr phi r. So if you add these two terms, what we are going to get, that f of r plus h phi r plus h minus fr phi r. Okay, that is equal to the sum of these things, correct? Okay, so because these two cancels, correct? So this thing we are going to use now. Why do we need to use this? Because we already have this term f of r plus h phi r plus h minus fr phi r. Okay, so here we are going to use the bullet point D to write down this addition of the derivatives and the error terms. Okay, so the term 1 as it is plus 1 over h, okay, and integration s to t capital T of t minus r, okay, as it is, and then now this difference is del tf. Okay, so del tf times h. So this h would actually cancel with this 1 over h later. So h plus now b r phi r. Okay, so this is the partial derivative with respect to time, and then this derivative with respect to the space. So br phi r times phi of r plus h minus phi r. So this is exactly obtained from verbatim from the point D, plus w1 and w2. I am not writing here its dependence on h and r, but that is understood, just to fit everything in the same slide. Phi w1 plus w2. So this integration is dr. Okay, so this term is elaborated here, and then we have this whole thing as term 2. Okay, I have written simply just term 2, and then minus this, then this integration s to t capital T of t minus r. Okay, so exactly what is written here, I am writing exactly the same thing here. I mean, no change here. So notice that here already I have a partial derivative with f and then b. So like these things are appearing here. So I mean, these two terms are coming when are looking very similar. Here only thing is that we have w. Here I have phi r plus h minus phi r. So that is the thing, we need to really check. So this is the main thing, main term, which would give me again WH. So I would get an equation in WH. Okay, so let us go to the next slide. So there we are going to write on term 1 plus term 2, and so term 1 plus term 2 plus this additional term here. So s to t integration capital T of t minus r del f del t, okay, minus, so as I told that, okay, this term and this term should be compared with, so del t f of r comma phi r plus h, whereas we have r comma phi r here. So here that's why we get del f del t r phi r plus h minus del f del t r phi r dr. Okay, so we call this whole thing as term 3. But we still have some more terms, because we still have b terms here that we are going to deal with now. But we can take b a term common, because here we have b. So this b term capital T of t minus r b r phi r. Here also we have capital T of t minus r b r phi r. Okay, there is a typo here. The bracket should this parenthesis should come here actually. Okay, so here, unlike here we had phi r plus h and r phi r. Okay, so here we both the cases we have phi r. Okay, so you can take common. Okay, good. So this term we call term 3, and we take common those terms. So integration s to t capital T of t minus r b r phi r, and then phi t plus h minus phi r plus h minus phi r divided by h. That comes from here, phi r plus h minus phi r, and then 1 over h is there, so divided by h comes from there. And here we just have wr. We don't have 1 over h, okay? We just have wr here. So the minus wr. Okay, so we got this term, but we know this term. Okay, this is precisely WHT. Okay, WHT, which we started with. The definition of WHT is 1 over h phi t plus h minus phi t minus wt. So that is the WHT. So this term is known. This is WHT. Okay, so what we have obtained the WHT is equal to term 1 plus term 2, where both the terms goes to 0, and the term 3. So here term 3 is also interesting. What happens here, that as h tends to 0, since f is continuously differentiable, that means derivative is continuous. So and phi is also a continuous function of r. Okay, so here this thing converges to this as h tends to 0. Okay, and this is bound linear map on this compact set, finite interval. So this whole thing converges to 0 as h tends to 0 using the bounded convergence theorem. Okay, so term 3 also goes to 0. Okay, and now the term 4, this additional term, what appears here that W and W2 also are present here in these terms. So that thing, would be a capability of T minus R composed on W and W2. Okay, so that should also be kept. So I have written the plus 1 over H integration small s to T capability of T minus R then of this addition of W1 and W2 here. Okay, so this is the expression of WH, and here's term 1, term 2, and term 3. For these 3, I have already argued that all these 3 converges to 0 as H goes to 0 in the monospace norm. And then for these, this is precisely WHT, so we are going to replace this by the WHT notation. And then term 4 already we have by virtue of the differentiability we know that these errors, okay, error terms 1 over H W1 goes to 0, 1 over H W2 also goes to 0. So 1 over H is appearing here, so 1 over H W1 or 1 over H W2 goes to 0. So then again use the boundary convergence theorem of integrals to ensure that term 4 also goes to 0. Okay, so what we have obtained is that WH is equal to term 1 plus term 3 plus term 4 plus some term where WH converges. So I write down this whole thing in a more abbreviated form. The WHT is equal to the sum of all these 4 terms, term 1, 2, 4, 1, 2, 3, and 4, and then this term, that is integration s to t, capital T of t minus r, b of r phi r as it is, and then this whole thing is by definition is WHR dr. So WH satisfies this equation, okay, this integral equation. Okay, so from here actually our main goal was to show that WH converges to 0. So from this I need to find out the norm of WH and need to show that norm of WH goes to 0 as H goes to 0. So we take the norm both sides then, correct? And then we don't need to worry about this. This is something goes to 0. So now as H tends to 0, this this norm of this thing, this whole thing I write down as epsilon. Okay, so norm of all these things, term 1, term 2, term 3, term 4. Okay, so these are actually the summation of these 4 terms. Actually a point in the monospace is a function of H also. As H goes to 0, that converges to 0, and the norm of that function we call this epsilon H. Epsilon H is a positive real number, non-negative real number. So what we know about these terms, that okay, this epsilon H goes to 0. Okay, so this property, this expression we are going to use now after when we take the norm both sides. Okay, if you take norm both sides, okay, so here norm of addition is less than or equals to addition of the norms, the triangular inequality. So we are going to get norm of WH is less than or equals to epsilon H plus capital M times M is something I'm defining later, integration s to t norm of WHR dr. Okay, so this WHR dr is here. So this thing, okay, so if we now upper bound this thing, this operator, okay, the norm of this operator. Yes, of course we can, because this is boundary linear operator, and these are also with respect to this time variable, these are also continuous. So we can actually take supremum over all R on this closed interval S to capital T. Okay, so this capital is some future time capital T, and then this capital is of course the semigroup. So norm of capital T of T minus S and norm of BR phi r, if we take this, we know for sure there is finite. We don't know exactly what value, but we know this finite capital M. M is finite. So that M I replace here to because I can do that because less than or equals to sign, right? You can replace by a larger quantity. Capital M times integration S to T WHR, okay, norm of that dr. So now this has a real valued function, correct? Function of time, because the norm I have taken a real valued function now, this whole thing. So this real valued function is satisfying this equation. The norm of, I mean, this thing is less than, the same thing appears here, correct? R is from S to T. So then we can use the Gronow's inequality. Thus, by Gronow's inequality, WHT, okay, can be written as, less than or equals to this quantity epsilon h times e to the power of this constant m times capital T minus s. Okay. Okay, if I put t is equal to s, then it is 0 here, so wh. So basically, I should have written wht minus whs minus epsilon h is less than, but that epsilon h anyway goes to 0, so it is not much is material. So norm of wh is less than or equals to this term. Here we see that this this is a finite quantity, and as h tends to 0, this epsilon h goes to 0. So here we conclude that norm of wh goes to 0 as h goes to 0, okay, for every small t, okay, in the interval small s to capital T. Okay, so by proving this, what we have done that we prove that Wt is Wt is differentiable, correct? Not Wt, phi is differentiable, because that was the main goal here. So we had to show that yes, WHT was this. So since we have shown that WH goes to 0, that implies that phi is continuously differentiable, and the derivative is W. Okay. Next, we know that Wt is continuous, since phi is continuously differentiable and W is a derivative of phi. Also, we know that W satisfies that equation. From that also we get that this is continuous. Okay, so continuous. So now we need to show that phi is a classical solution. Okay, so here till now what we have proved is that phi is differentiable. Okay, but we would like to show that this is the right candidate, where phi was just the mild solution I have taken, correct? So, and we have shown that the mild solution is sufficiently smooth, that means it is differentiable. But then what is the guarantee that this mild solution, which is actually solution of the integral equation, indeed solves the evolution problem, okay, classically? So we need to do that. So to show that phi is classical solution, we consider another equation. So d psi dt, okay, exactly the same operator A, d psi dt is equal to a psi t plus f of t comma phi t, psi s is equal to x. See, here I have kept the same phi. This phi is the mild solution of the semilinear evolution problem, SEP. Okay, so I kept phi. So phi is considered here as known. Okay, and we have already proved that the mild solution is sufficiently smooth. So we know a lot about the function phi. So that f of t comma phi I am considering is a known quantity, and unknown psi appears here. So it's a new equation actually. This is not the same equation there. So we call this equation as the start, okay, denoted by star. And starting psi s is equal to x, the same initial condition, okay. Now for this is nothing but IIVP. It is inhomogeneous initial value problem, where this f is very nice because phi is differentiable, f is also differentiable. So, so f of t comma phi t is differentiable. So as a function of time t, it is differentiable. Okay, so from that, so I write down here this thing that R2 f of R phi is in C1. So from that, we can apply now the regularity theorem for IIVP that asserts that this equation has a classical solution. Okay, let us call that classical solution as psi. Okay, so hence this star has a classical solution psi, and then this psi also I mean, we know that that it has a classical solution, and the classical solution can be written using the formula for variation of constants. So the variation of constant, the formula we write down here. So psi is given as psi t is equal to the semigroup generated by the operator a t minus sx plus integration s to t capital T of t minus r, and then this additive term f of r comma phi r dr. So remember, this phi is kept intact there. So psi is equal to this thing. However, this is something which we have seen earlier. So what is this? We have already seen that the ACP has a mild solution, we have already seen, and that mild solution satisfies an integral equation, and that integral equation exactly looks this. Okay, and here we have exactly that mild solution is appearing here. So we know that for the mild solution, okay, phi satisfies this integral equation for each and every time t between s to capital T. So this whole thing as a function of t is nothing but the same as phi t. After studying this, what we have obtained, the psi t can be written this way using the formula for variation of constants, and then we recall what is the mild solution of ACP. The mild solution satisfies some integral equation, but here in that so this appears on the right hand side, this appears on the left hand side there in that mild solution. So let me write down, let me show you that again. Yes, phi of t is equal to tt minus sx integration s to t capital T minus r f r phi r dr. So this phi appears. So now even if I hide it, so if I take the solution of this equation, which is the mild solution, and plug in here, I would get something which would exactly match with this phi t for all time t, correct? So that appears here exactly. So this thing, tt minus sx integration s to t capital T of t minus r f r of phi r dr. So this appears here. So that mild solution integration that appears here, so that is equals to phi t. So what you have obtained is psi is same as phi. Okay, so for all t greater or equals to s in between s to capital T. Okay, so this is psi and phi are equal. So what does it mean? That means that the mild solution of the ACP, okay, is indeed the classical solution of this. So that means this phi satisfies this. That means I could be able to write down d phi dt, so it satisfies classically. So I can replace psi by phi here, because psi and phi are same. So you get d phi dt is equal to a phi t f t phi t. Okay. Earlier I could not, because here by fixing phi here, I know that it has a classical solution, and this relation is satisfied by psi classically. And when we have that, then we show that this psi is same as phi, and then we can conclude that okay, phi solves this classically. Okay, the argument has some steps and some steps. Okay. So we are done. So thus phi solves this star classically. But what is this? This is exactly the ACP. If I so phi solves this classically, if I replace phi here, so it is d phi dt plus is equal to a phi t plus f of t comma phi t. So that means phi solves this classically. Okay. Good. I mean, of course, the way we have proved, it does not prove uniqueness. Right, because here I just show that okay, the phi, if I replace phi, then it solves. but it does not, but I'm not saying that whatever solution it may have, classical solution, you know, of the ACP, that would have you know, this particular formula or anything. So here, I mean, this roundabout way we have obtained just the existence of the solution of ACP. Okay, thank you very much. So by this I am finishing this portion of the semilinear evolution problem. Okay, thank you.